Hello chemists, this is Ms. Placino and you are watching Screencast 2.2 on the Bohr model of the atom. In today's lesson we're going to address how the idea that energy is quantized impacted the model of the atom. In the previous lesson we talked about what it means for energy to be quantized, but I want to take just a minute or so and quickly review that. In the last lesson I used a ramp and a staircase to help illustrate what we mean when we say energy is quantized. You might remember that the ramp represents continuous energy, or the idea that energy is continuous. And the staircase is our quantized view of energy. On a ramp, there are really no limitations about where you can stand. You can be on literally any point of that ramp, and you're going to be able to exist there. However, in a quantized view, or the staircase model, there are very specific locations that you can occupy. For example, you can stand on the first step or the third step, but there is no way for you to hover on, say, the 2.4 step. It doesn't exist, therefore you can't be there. The model of the atom that scientists are working with at this point in time is the nuclear model, proposed by Ernest Rutherford, which says we've got this positively charged mass, the nucleus, at the center of the atom, and then our electrons are just kind of scattered randomly throughout. The observation that energy is quantized is going to change the scientist's view of the atom. It has to evolve so that we can take into consideration this new information. Now, the idea that energy is quantized wasn't just being shown through the photoelectric effect. Scientists were also observing it as they looked at different energy that was emitted from excited gases. So we'll talk a little bit more about that in just a second. If you take white light and you shine it through a prism, something you probably did in elementary school or middle school science class, you know that the prism is going to separate that white light into all the different colors of the rainbow, everything that we can see from about 780 to 380 nanometers. We look at the nuclear model of the atom one more time. We know that there are really no rules about where the electrons can be. So when we take a gas, something like hydrogen or helium, and we excite it, basically just by passing an electrical current through that sample, it causes the electrons to gain energy and move farther away from the nucleus. When they come back closer to the nucleus, they're going to release that energy. If there are no rules about where the electrons can and cannot be, in theory you should see all the colors of the rainbow as those energy transitions occur, energy is given off, and you should get every possible color that we can see. However, when scientists perform this, instead of seeing a continuous spectrum, they see what's called an emission spectrum. And this is the light that is emitted from that excited gas. Again, a sample that we've just passed an electrical current through. It glows and it gives off that energy as light. And when you take the light and you pass it through a prism, instead of seeing all the colors of the rainbow, a continuous spectrum, you see very specific lines. This is called the emission spectrum. So it turns out that every element on the periodic table has its own unique emission spectrum. So by looking at an emission spectrum and comparing it to knowns, you could actually go through and identify what element you are looking at. This is how scientists in more recent times have been able to figure out what things like the stars and the sun is made of. Hopefully it goes without saying that no one's been to the sun to take a sample, but we can look at the light emitted by it, and we can see that we get the same characteristic spectrums of things like hydrogen and helium. So this is more proof that energy is quantized. So scientists are at a bit of a loss. We've got the nuclear model of the atom, but it doesn't seem to be working out so great. Enter Niels Bohr. Slightly after the nuclear model was proposed, Niels Bohr proposed the planetary model of the atom, also known as the Bohr model. We'll use them interchangeably here. The Bohr model took into consideration the fact that energy is quantized. So instead of just the electrons being able to exist all over the place, there are rules where they can exist. So if we think about that staircase and the rules, Bohr basically takes the staircase and he turns it into rings. Oops, that's a terrible looking ring. Not that that's much better. So instead of the electrons just being anywhere, they are going to be, and I'll just use dots to represent the electrons, somewhere on these rings. And now it's called the planetary model because the nucleus is at the center of the model and the electrons orbit around it, just the way the sun is at the center of the solar system and the planets orbit around it. So let's talk a little bit more about the Bohr model. Here's another picture of it. We got the nucleus. We know that's positively charged. At this point in time, scientists still don't know there are protons and neutrons in there. They just know it's positively charged. And hopefully it goes without saying that this is not drawn to scale. The nucleus is extremely small. These rings are called orbits, and they are the paths that electrons travel in. Please note that because energy is quantized, an electron has to sit in one of these orbits. It's not possible to put an electron, say, there. That's not on the second ring, it's not on the third ring or orbit, so it cannot exist. In fact, nothing at all exists in between the nucleus and that first orbit, and in between consecutive orbits. Nothing is there, not even air. Air is too big, molecules of O2 and N2, to fit in between the nucleus and the different orbits within the Bohr model. So a little bit more about the Bohr model of the atom. There are rules about how many electrons can fit in each orbit. And if you think about it, we'll go back to that picture for just a moment. As you get farther and farther away from the nucleus, those rings get bigger and bigger. So in the first orbit, we can only hold 2 electrons. In the second orbit, we can hold 8. A total of 18 can go in the third orbit, and the fourth orbit can hold 32. We're not going to worry about getting too much farther than that. You might be wondering how the electrons are going to fill the orbits. Well, it turns out that the electrons are going to be as close to the nucleus as they possibly can be. And then once that orbit fills up, then you back up to the following orbit. And when all the electrons are in the lowest possible orbit, we call this the ground state configuration. And if you take a look at your reference table and you look at the periodic table, at the bottom of each little element box, you are going to see a string of numbers. That corresponds to the electron configuration, specifically the ground state configuration according to the Bohr model of the atom. I want to talk a little bit more about how those emission spectra are produced. So we've got an atom in the ground state, where the electron is as close to the nucleus as possible. And based on the picture, we can see that light energy, well, maybe you can't see so well, is being absorbed or going into that electron. If I was to write the electron configuration, I'd see that I've got 1 electron in the first energy level, and I've got no electrons in the second or third. So I could write that as 1, 0, 0. Usually we won't write these 2 blank zeros because there's nothing in it in the ground state, but we will just for the purpose of this exercise. When the electron absorbs energy, it's going to move further away from the nucleus, and it enters the excited state. If we were to write an excited state configuration, it would look like that, 0, 0, 1. That same electron has moved farther away from the nucleus. Now it's still the same atom. It hasn't really changed other than the fact that now one of its electrons, or its only electron, has been excited. So in order to enter the excited state, an electron has to gain energy. And as it gains energy, it's going to be able to be promoted to a state or an orbit that's farther away from the nucleus. Please note that this is like an exact change vending machine. The energy being absorbed by that electron has to be the right amount to promote it to another orbit. If it's too small or too big, so too much or too little energy, then the electron isn't going to move. It's very selective, so it has to be the exact amount of energy that's needed to promote it to another orbit. If it's going to put it somewhere in between, let's say here, that electron is not going to move because energy is quantized and it cannot sit in between 2 orbits. All right, so we're in the excited state. Eventually, that energy is going to be released. So this time we have energy going out. That energy is released as light, and that's what scientists are passing through a prism so that they can see what color it is. This is a return to the ground state. So in order to get to the ground state, the energy is going to give up that energy. That energy is emitted as light, and the electron returns to the ground state. Now you might be able to imagine that different energy transitions, or going from different orbits, is going to create different amounts of energy. So if I go from the second back to the first, that might be different than going from the third to the first, or the third to the second. And that's how we get the individual lines of the spectrum. Now in reality there are even more transitions that are occurring, but they're not going to fall necessarily within that part of the visible spectrum that we are able to see. All right, so before we move on to anything new, I want to talk a little bit more about ground state versus excited state and do some practice with that. So let's take a look at your practice problems. I want to look at just these first three: argon, manganese, and aluminum. And for each of these, I want you to write the ground state and two possible excited states. The ground state comes directly from your reference table. If you look at the element box for argon, and you look at the very bottom, you see the string of numbers, and that corresponds to the ground state electron configuration for argon. Argon with its 18 electrons goes 2-8-8. That is the ground state. There is only one possible ground state for each element. Excited states are different. We know that we're going to take one of our electrons from the ground state and promote it to a higher energy level or a higher orbit. There are almost an infinite number of excited states for an element. So for example, I could go 2-8-7-1. It's still argon, but I've taken one of the electrons and I've promoted it to a higher orbit. Only really two rules to keep in mind. Number one, make sure you have the same amount of electrons. I've got 18 in each case. And number two, make sure that you don't break the 2-8-18-32 rule. What I mean by that is something like 198 is not a valid excited state. The second energy level cannot have 9 electrons in it. It fills up at 8, so I've broken a rule, so this is invalid. Let's get rid of that. Something like 1-8-8-1, that would be fine. Why don't you go ahead and pause the video, see if you can come up with a ground state and two possible excited states for manganese and aluminum. Let's check your work. All right, so manganese, its ground state has to be 2-8-13-2. And remember, your excited states don't have to necessarily be the same as mine. Just make sure that they add up to the correct number of electrons and that you haven't broken that rule above. So I came up with 2-5-16-2. I promoted a bunch of electrons to another energy level. That's still an excited state. 1-8-14-2. There's another possible excited state. Aluminum, only one possible ground state. 2-8-3. Possible excited state might be 2-7-4, or maybe something like 0-8-5. Again, there are many different excited states for each element. Just make sure that you're not breaking the 2-8-18-32 rule. All right, so let's get back to your lesson. The last thing I want to talk about is really more of an advanced concept than what you need for traditional intro-level chemistry. I'm going to talk about using this equation known as the Rydberg Equation. If you Google the Rydberg Equation, you'll probably find other variations of it, but this is what we're going to use in this class. So this R sub h, that's the Rydberg constant, is 2.180 times 10 to the negative 18th joules. H is Planck's constant, 6.626 times 10 to the negative 34th joules seconds. And just to give you a little bit more information, it's not on the slide, we know that V is frequency. We're going to see that in hertz, which is equal to 1/seconds. And then N low and N high, this represents the lowest, or the lower, I should say, orbit. And N high represents the higher orbit. This is actually a pretty cool formula because based on its, what we use it for is to predict what the frequency of the light that is released by a certain transition is going to, what it's going to be. So I have the low orbit, so where is the electron going to and where did it come from, and I can mathematically determine the frequency and therefore the color of the wavelength that is, of the light that's going to be produced by this transition. I know this formula looks a little complicated, but I promise it's not too bad. Let's head on back to the practice problems and try one of these out. So we'll look at question 3. It says an electron moves from n equals 5 to n equals 3, so from the 5th to the 3rd orbit. What is the frequency of the light emitted? Well, in order to figure that out, we need to use the Rydberg equation. So we've got frequency is equal to the Rydberg constant divided by Planck's constant times 1 over the low orbital squared minus 1 over the higher orbit squared. We're trying to find frequency, so we don't have that information. R sub h is a constant, 2.180 times 10 to the negative 18th joules. Planck's constant is, of course, a constant. Times 1 over, in this case, our low orbit. Smaller of the two numbers is 3. And our high orbit, the larger of the two numbers, is 5. Be careful about how you punch things into your calculator. It's really easy to kind of make a mess of things. But once you've got everything plugged in there, you should end up with a frequency of 2.34 times 10 to the 14th hertz. I'm not going to go through and do parts B and C of this problem as it was addressed in a previous lesson, but just really quick to make sure we're on the same page. If you're trying to find the energy of the light emitted, what formula could we use there? Hopefully you're thinking E equals hv. We know Planck's constant. We have just calculated frequency, so we should be able to solve for energy. And if I want to find the wavelength of the light that's going to be emitted, if I'm interested in knowing the color that is going to be emitted, what formula can I use? Hopefully you're thinking C equals lambda v. Speed of light is a constant. V has already been calculated, so you could just plug in and solve for the wavelength. Nice review of stuff that we covered earlier this unit. All right. That wraps up today's lesson. You should really try to take a minute or so to write a 2-sentence summary of what we talked about today. I know some of this can be confusing. Make sure that you feel comfortable with the ground state and the excited state and understand the energy transitions that take place. Don't get too overwhelmed by that formula. We'll do more practice with it in class. All right. Thanks for tuning in. I hope this was helpful.